Okay, in this problem, we know the mean height of 3-year-old boys in the United States, but we want to know if boys born outside the United States have a significantly different height or not. Okay, and so the problem says that in the United States, the mean height for 3-year-old boys is 38 inches. Okay, and then we've taken a random sample of 15 boys not from the United States. The sample mean was 37.2 inches, so that's my x bar, and my sample standard deviation, that's my s, was 3 inches. Okay, so please make sure that when you read a problem, you can identify each of the variables and be able to assign them to the numbers. Part A says determine whether the population mean is significantly different for non-US boys than it is from US boys. Okay, so this is for boys from the United States, and these are non-US boys. So the null hypothesis, okay, we're going to use the data here, and based on the data on our sample, we're going to try to make an estimate about the mean height of boys born outside the US. Okay, so mu represents mean height of non-US boys. Okay, and we want to know, is this significantly different from 38 inches or not? So the null hypothesis would be that the mean height is the same as it is for the United States, meaning that mu is 38 inches, the mean height of non-US boys, 38 inches, and the alternative is that the mean height is not 38 inches. Okay, and so and that's just because in the words in part A, it says if it's significantly different. So you just see the word different. So it's not saying is it higher or lower, it just says different. So we've got a not equal to sign. So when you see different, use not equal to sign, and that means we have a two-tailed or two-sided test. We've got to figure out our test statistic, which is, as always, the observed statistic, observed minus what's in our null hypothesis, divided by the standard error. What was the mean that we observed? We observed a mean of 37.2 inches. What's stated in the null hypothesis? 38 inches. And what's our standard error? In this case, standard error is always s over the square root of n. That's for whenever you're doing a t-test for one sample. So our s over the square root of n would be 3 divided by the square root of 15. 37.2 minus 38 gives me negative 0.8 on the top, and on the bottom I have 3 divided by the square root of 15, which gives me 0.7746. Okay, so if I'm going to just do negative 0.8 divided by the answer button. I don't have to worry about rounding, and I get a t-statistic of negative 1.033. So here, I'm going to look this up in my t-table. And to do this, I have to figure out my degrees of freedom. So if my n is 15, my degrees of freedom is 14. And I go over to my t-table, and I'm going to go to the row that says 14 degrees of freedom, and I want to see where this number fits. 1.033. So again, the t-table only shows positive numbers. So I'm just going to ignore the sign here. Okay, so for 14 degrees of freedom, the smallest number I see is 1.345, and the next number is 1.761. 1.345 corresponds to a tail probability of 0.100 and or 10%, and 1.761 corresponds to a tail probability of 0.05. Okay. So my number 1.033, if I were to put it in the lineup, would be right there. Smaller than 1.345, which means my tail probability would be greater than 10%. Okay, so in this case, what this is saying is that if I draw a line at negative 1.033, I have whatever this is, this tail, it's more than 10%. So for a two-tail test, I've got to double it, because I also have more than 10% in this tail. So my total p-value, whatever it is greater than 20%. Alright, and so it says use a significance level of 5%. So significance level is alpha. Alpha is 0.05. Here our p-value is greater than alpha. Our p-value is 20%, which is bigger than 5%. So this means we do not reject the null hypothesis. And this means that after looking at a sample of 15 kids, and I see that the sample average is 37.2, it's not significantly different from 38. Okay, so we do not have evidence that the mean height of non-US boys is different from US boys' mean heights. Okay, so that's that problem. Then part B asks us, suppose the sample consisted of 30 boys rather than 15. Okay, so we're going to pretend that we have the same data. We ended up with a mean of 37.2, standard deviation of 3, but this time our n is 30. Okay, so we're going to go through the same process, except some of our numbers are going to change. Okay. So everything, the test statistic is still going to be observed minus the null divided by our standard error. The standard error, however, is still s over the square root of n, but now my n has changed, so my observed is still 37.2, my null hypothesis still states 38, the standard error is still s over the square root of n, my s is 3, and the square root of n is now going to be the square root of 30. So up here I have negative 0.8, and 3 divided by the square root of 30 is equal to 0.5477. And so doing that, I get a test score of 1.46, negative 1.46. Now I have 29 degrees of freedom. Okay, n minus 1. I had 30 in my sample, so now I have 29 degrees of freedom, and I'm looking up the value 1.46. So if I look, I have 1.311 and 1.699. 1.699 corresponds to tail probability of 0.05, and this corresponds to tail probability of 10%. And so 1.46 now fits in between there. So my tail probability, whatever it is, it's more than 0.05, but less than 10%. So again, looking at our picture, when I draw a line at 1.46, this area, I don't know exactly what it is, but it's more than 0.05, but less than 10%. So maybe it's at 6%, 9%, whatever, something in between 5 and 10%. But I've got two of these because I've got a two-tailed test. The not equal to sign means I've got a two-tailed test. So my total p-value is going to be more than 10%, but less than 20%. Okay? Again, I'm looking at alpha equal to 0.05, and so I still make the same conclusion. do not reject the null hypothesis, which means I still do not have evidence that the mean height of non-US born children is different than the mean height of US boys. And part C asks us to explain why the t-values and p-values for parts A and part B are different. Okay, so what's happened is we've changed n. So part C, we changed n. Okay, so in part B, the standard error was smaller. Okay, when we made n larger, the standard error got smaller. So this difference of 0.8, okay, when the standard error was large, it was only it was not that many standard deviations or standard errors away from the mean. When the standard error gets smaller, then that distance of -0.8 gets farther and farther, more standard errors away. So we were more standard errors from the mean. Okay, and that in turn will reduce our p-value. That's that problem.